Hello everyone, welcome to this video. In this video we shall see some more problems of ordinary differential equations where the solution of such equations are found using Laplace transform. So let us have a look at our first question. It says that you have to solve this differential equation whenever you are given the initial conditions y of 0 is equal to 1 and y dash 0 is equal to 0. So these two conditions are given to you. That means your given differential equation is initial value problem. And in this case, this delta t and delta t minus 2 that represents the Dirac delta function. Now finding the solution of such equations is not so easy using the analytical methods or by any other method. So this technique for Laplace transform is very useful in this particular case. So what we are going to do, we are going to apply the same steps. That means we'll first apply this Laplace transform on both sides of the equation so that we will obtain the Laplace transform of y double dash as s square y dash minus sy of 0 minus y dash 0, and instead of this Laplace transform of y dash, its value would be this, and because we have assumed Laplace transform of y that is equal to y bar, so this is equal to this, and moreover the Laplace transform of this Dirac delta function delta of t that is equal to 1. This is according to formula that we already know, and the Laplace transform of Dirac delta function shifted by 2 units, that is going to be e to the power minus 2s, because a here in this case is 2, right? So accordingly this will become 1 plus e to the power minus 2s, right? So now we can substitute the values of y of 0, y dash 0 and y of 0 here. The values are given to be 1 and 0. So we'll substitute its value as 1, its value as 0 and its value again as 1. And when you simplify this expression in terms of y bar, you will have expression of this kind. So that means now we are ready to calculate what is the inverse Laplace transform of this particular expression. Our inverse Laplace transform would be obtained when you apply the inverse Laplace transform operator on both sides of this equation, and because we know its inverse is going to be the function y of t, which is the solution of the given differential equation. So let us apply that, right? So before applying that, what we are going to do, we are first going to evaluate these terms into more simpler terms, right? So we are converting this into two different factors, into these and into these. So our next task is to apply partial fractions in order to separate out this term. Okay, so we'll first apply the inverse Laplace transform. So once you apply this, here it comes out to be 3 by 2 e to the power minus t minus half e to the power minus 5t minus 1 by 4 u of t minus 2, where what is this u? This is the unit step function displaced by 2 units to the right into these functions. Now how do you end up from this to this expression, right? So this is the question, how? So to answer that, we'll go individually. So I'm calling this first factor as our factor number 1. So we'll obtain its Laplace transform first, inverse Laplace transform. So that would be given by this expression over here. So it is going to be, firstly we have to perform the partial fraction for this fraction s plus 7 divided by s plus 1 into s plus 5. So that comes out to be this 3 by 2 divided by s plus 1 plus minus 1 to the power 2 s plus 5. So this is very simple. You will write this to be a upon s plus 1 and b upon s plus 5, and accordingly you obtain these coefficients as 3 by 2 and minus 1 by 2. So once you obtain these coefficients, you will apply the inverse Laplace transform, and its inverse Laplace transform 3 by 2 is constant, would come outside. So the inverse Laplace transform of 1 divided by s plus 1, that is equal to e to the power minus s, and according to formula this is equal to e to the power minus 5t. So this is the inverse Laplace transform for this particular function. So we end up here. Okay, so moving on to the second term, we have to obtain inverse Laplace transform of this particular quantity. So again what we will do, we will apply partial fractions onto this particular term so that you obtain the value of a as minus 1 by 4 and you obtain the value of b as minus 1 by 4 again. So we just substitute the values here and then we perform the inverse Laplace transform of both terms, right? So because of linearity we can separate out the terms and we can apply the second shifting property here. What does the second shifting property says? It says that whenever you have the function f of t and you define the you define the Laplace transform of this function f of t as capital F of s. In that case, the inverse Laplace transform of e to the power minus as f of s, that is equal to the unit step function displaced by a units, whatever is the coefficient of s here in this term, into the inverse Laplace transform of this function again shifted by a units to the right. So this is according to second shifting property. So using that, because we know the inverse Laplace transform of 1 by s plus 1, that is equal to e to the power minus t, right? And because you have this term over here, so that means whatever is your answer, you multiply that by this unit step function displaced by 2 units, and instead of this 2 you will write instead of this t you will write t minus 2 over here. So this is how you obtain this expression. And similarly for the second expression, we know the inverse Laplace transform of 1 by s plus 5, that is equal to e to the power minus 5t. So instead of writing this t here, because of the presence of this term, using this second shifting property, we'll obtain the unit step function displaced by 2 units and then this value e to the power minus 5 t minus 2. Okay, so this is how we obtain the inverse Laplace transform for this second term also. So this term also, right? So this is y of t. So our final answer is equal to the expression given by this term. So we have, so this is our final answer, right? Y of t is equal to 3 by 2 e to the power minus t minus 1 by 2 e to the power minus 5t minus 1 by 4 u of t minus 2 e to the power minus t minus 2 e to the power minus 5 t minus 2. So this is our final answer. Let us have a look at our next question. It says that solve the following differential equation. Now this is a differential equation where the coefficients are not constant. So this term is being multiplied by 2t here. Here y is your dependent variable and t is the corresponding independent variable. So here, in order to solve this equation, we have to use this property of multiplication with t. So when you take the Laplace transform of this equation on both sides, so basically what we are doing, we are taking the Laplace transform for the individual terms because this is a linear operator, and then we know if you define the Laplace transform of L of y to be y bar, right? So its first derivative is given by this expression, this you already know, of second is given by this expression, and so we can substitute in place of this function this quantity in place of this function. Now here we have to apply this formula, multiplication with t. You know the Laplace transform of t into y dash, that is equal to minus d ds of the Laplace transform of y dash. So that means whatever is this Laplace transform, you will differentiate it with respect to s. That what multiplication by t tell you. Okay. So here you will obtain the Laplace transform of y dash into and you have to perform its derivative with respect to s. So you can substitute the constants here. These are given to you in the equation. Y of 0 is given to be 0 and y dash 0 is given to be 1. So when you substitute these quantities here and here, and here also, right? So you obtain this term. Now when you simplify this in terms of y bar, so you see at the end you will get a differential equation, first order differential equation in y of s. So that means because here we are to simplify this expression in terms of y dash, y bar, right? So we have to solve this differential equation. Now this is a linear first order differential equation. So we can solve this by the method of integrating factor. So this equation is in this form: y dash plus py is equal to q. So its integrating factor is given by e to the power integration p, whatever is the independent variable, right? And its solution is then obtained by making the equation exact, right? So we have calculated according to this the expression I have written over here, and this is the integrating factor, so that its solution becomes this integrating factor multiplied by the variable, that is equal to integration of integrating factor multiplied by this right hand side expression. So the next task is to simplify this and solve for this y bar s. So what do? We multiply the terms containing s, and then we make this substitution: s square is equal to 4z. So when you make the substitutions, your ds become equal to dz by square root z. So you can substitute all these quantities here. So your left hand side would remain unchanged, but you are making the substitution on the right hand side, so this become equal to this particular quantity, right? So now you just have to solve these powers, and then you have to just simplify all these powers, and then your expression would be something like this. So you have these two terms. Now what you can do, you keep this term as such, and then you perform the integration of this term, so that whenever you consider this as the first function, this as the second function, this would result in this particular kind of term. So let's see how. You keep this term as such, there is no changes, and here the first function as such, integration of second minus integration derivative of first, integration of second. So if you look at this carefully, this term cancels with this particular term. How? When you multiply this by 1 by 2, so this term is exactly the same term with an opposite sign. So that means we are only left with this particular quantity. So now we can make the substitution back, so that instead of z we can write s square by 4. So our final right hand side becomes equal to this particular quantity. So therefore you have the value of y bar s is equal to this quantity plus c. So this is what you have. So now you see this and this, they nullify each other, cancel out each other's effect. So we are left with this simpler expression. So now the next task is to apply inverse Laplace transform on both sides. So when you apply inverse Laplace transform, you obtain this expression as y of t, and here you obtain the Laplace inverse of this term as to be t, and the Laplace inverse of say c, where c is this constant of integration. So it could be another constant, you can write that by d, and actually this constant would tend to 0 because your yt will tend to t whenever your s is going to infinity, right? So this is your final solution. Alright, let us now move on to our next question, which says that solve the equation by the transformation method. So we'll apply the Laplace transform here to solve this particular differential equation. So this differential equation, where we obtain the derivative as well as the integration term, is difficult to solve otherwise. So what we will do, we will apply the Laplace transform here, because we already know how can we calculate the Laplace transform for derivatives. And in addition to that, we also know how to compute the Laplace transform of integrals, right? So knowing all these things and making use of this, we can solve this very easily. So here the Laplace transform of y of t is given by y bar s. This is our assumption. So in that case, when you apply Laplace transform onto this equation on both sides, so you have the Laplace transform for this derivative plus the Laplace transform of y, that is so let me go term by term. So when you solve the derivative for this first term, that is going to be equal to this particular quantity, and you can substitute the value of y of 0. This is given to you as 1, right? And for the second term, the Laplace transform of y comes out to be y bar. For the third term, the Laplace transform of integral, that comes out to be the Laplace transform of this quantity divided by s. And the Laplace transform of sine t, that comes out to be 1 divided by s square plus 1. So now we can simplify our expression for y bar s. So we can obtain its value. It come out to be, after simplification, this term, right? So we can apply partial fractions and we can separate out the terms so that its Laplace inverse is calculated very easily. So when you calculate the inverse Laplace transform of this particular term, you will apply this inverse operator on both sides of this equation, so that on the left hand side this term becomes equal to your solution y of t, and on the right hand side you have e to the power minus t, e to the power minus t into t and sine t. Why this is so? Using the first shifting property. So accordingly this is your answer and solution to the given differential equation. And now let us have a look at our last question, which says solve the following differential equation using Laplace transform. So in this case, this third order differential equation is given to you, where y of 0 is given to be 1. The first derivative at the point t is equal to 0 is given to be 0, and the second derivative at the point t is equal to 0 is given to be minus 2. So this is given to us, and we have to find its solution. In order to calculate its solution, we write our given equation, then we apply the Laplace transform on both sides, so that we'll use this formula for third order derivative, this formula for second order derivative, this formula for first order derivative, and we also know multiplication by t square onto of some function y of t, and then taking its Laplace inverse results into this expression. So we'll use all this formula so that your Laplace transform of first term is this one, right? The Laplace transform of second term is this. For third term it is this, and you have on the right hand side t square e to the power t would be the second derivative with respect to s of the function 1 divided by s minus 1. So next you substitute all these constant quantities given to you in the question, the value as 1, 0 and minus 2 here, so that here you will substitute y of 0, this term and this term. Again for the second term you will substitute the value this one, and for the third you will substitute this value, so that you obtain 1, 0 and minus 2 here, 0, 1, 0 here and 1 here. So when you simplify this in terms of y of s, finally you will obtain the expression here of y of s to be equal to 2 divided by s minus 1 cube minus 2 plus s square, right? So this is the expression finalized. So we have the finalized expression for y of s to be this particular quantity. Now the task that is remaining is to apply the inverse Laplace transform on both sides for this particular expression. So when you apply inverse Laplace transform on both sides, on the left hand side this expression turns out to be the solution y of t, and on the right hand side its derivative, its Laplace inverse is simply, here you have to first apply the first shifting property, which says if the Laplace transform of f of t is given to be capital F of s, then the Laplace transform of e to the power a t f of t, that is equal to the Laplace transform of the same function shifted by a units. Now you have minus 1 here, so that means you will obtain the value 1 here according to that, and the Laplace transform of 1 to the power s by 6, that is equal to, the inverse Laplace transform of this quantity is equal to t to the power 5 divided by 5 factorial. So this is how you reach at this particular expression. Similarly here you will first apply this first shifting property. So according to that, you have e to the power t and the Laplace inverse of 1 divided by s cube, which turns out to be this t square divided by 2 factorial. And then you have to calculate the Laplace inverse for the quantity s square divided by s minus 1 whole cube. So here, in order to make the denominator and the numerator equal, we have this is done by ourselves, minus 1 plus 1, so that when you open up the square, you obtain these terms cancelled out, right? So now it is very easy to calculate their Laplace inverses. So the Laplace inverse for this first terms comes out to be e to the power t into 1, then e to the power t into t square by 2 factorial, and then 2 e to the power t into t, again using the first shifting property. So this is the final answer of the given third order linear differential equation. So I hope this topic is clear to you. How can you solve differential equations using Laplace transform? And moreover, in certain cases, it is very convenient to use this Laplace transform for finding the solutions of various kind of differential equations. Well, that is it for this video. Thank you for watching.